Review video 26, Bronsted-Lowry acids and bases. So, in my last two videos, we focused mainly on areneous acids and bases, and if you recall, areneous acids and bases is just one definition, one way to be acidic or basic. But you can define acids or bases in different ways, and Bronsted-Lowry is the other one we're going to pay attention to. So, if you have a substance that can potentially donate a proton, that substance is defined as a Bronsted-Lowry acid. If you have a substance that has room to accept a proton from somewhere, then that substance is a Bronsted-Lowry base. Now, I want to just specify, the H+ ion is a proton. And the reason that that is a proton is because hydrogen only has one proton and one electron most of the time. So once it ionizes and loses that electron, the only thing left is a proton. And so you're going to see the word hydrogen ion, H3O+, and proton used a lot in the same context, so you need to be familiar that a proton means a hydrogen ion. So, looking at that, because I know that a Bronsted-Lowry acid needs to be able to donate a proton, it has to already have a hydrogen to lose during a reaction. And because I know that a Bronsted-Lowry base has to accept a proton, that means that it needs to have room to accept a proton from somewhere else. And so when you're looking at substances, it is possible to kind of make a guess as to how a substance is going to act, but you cannot know for sure unless you have a whole reaction to look at. Because what you have to do is you have to track where the hydrogen ion is moving throughout the reaction. And in so doing, once you're able to figure out where that hydrogen is coming from and going to, you can identify your Bronsted-Lowry acid-base pairs. All right? So, let's talk really quickly about conjugate acids and conjugate bases and just define those. So, we already know that a Bronsted-Lowry acid has to lose a hydrogen. It has to donate it somewhere. Once it does that, it's going to turn into a conjugate base. So once again, a Bronsted-Lowry acid is going to turn into a conjugate base. So let's look at that process. Let's take sulfuric acid, H2SO4. H2SO4 is an acid. It's an areneous acid, and it's also able to act like a Bronsted-Lowry acid because it has hydrogens that it can lose. So once it gets rid of one of those hydrogens, you can see this 2 here disappeared on the other side. What it has turned into is a conjugate base because H2SO4 and HSO4- are almost the same compound. HSO4- is just missing a hydrogen. So literally the acid has turned into a conjugate base over here. To identify a conjugate base, you'll notice that most of the time their charge is going to be more negative than the original acid. Looking at our conjugate acids though, that is what a Bronsted-Lowry base turns into after it has accepted a hydrogen. Because again, we know Bronsted-Lowry bases want to accept a hydrogen. Once they do that, they turn into a conjugate acid. So over here we have water. Water is a unique substance for a reason I'll talk about in a little bit, but water is able to accept a hydrogen. And because it can do that, it's originally going to act like a base. And then once it's accepted that extra hydrogen, we can see the 2 turning into a 3, it's turned into a conjugate acid. And you'll notice that when you see these, their charge are going to be more positive than the original base was. So we can see that this one had a neutral charge, whereas H3O+ has a positive charge. All right? Last type of substance I want to talk about is an amphoteric substance. And amphoteric substances can act as either a Bronsted-Lowry acid or as a Bronsted-Lowry base, depending on the situation that you put it in. And the most famous example of this, the one that you're going to see a lot, is water, right? Water is a little bit special because in the areneous sense of the definition, water has both a hydrogen and a hydroxide. So we can define it as either an areneous acid or an areneous base, but it has the capability to donate a hydrogen and also accept one, which means it can be either a Bronsted-Lowry acid or a Bronsted-Lowry base. Because if we see water in the center, if it loses a hydrogen, then great, it can act like a Bronsted-Lowry acid. But if it gains a hydrogen and accepts one from somewhere, it can act like a Bronsted-Lowry base. So again, amphoteric substances can do either one, and water is your best example here. There are a few other substances that can do that as well, like amino acids have a bit of amphoteric character to them, but water is the one that you need to be worried about. All right. Also, when you're looking at a Bronsted-Lowry reaction, it is actually possible to predict the direction that a Bronsted-Lowry reaction will go, because most of these reactions are at equilibrium and could theoretically proceed in either direction. Basically, if you see a strong acid or a strong base, the reaction is going to move away from that thing. And if you don't see a strong acid or a strong base, but you do see H+, H3O+, or OH- in that reaction, you're going to treat those things as if they were the strong substance present. The reason that reactions proceed away from H+, H3O+, OH-, or anything that happens to be strong is because of Le Chatelier's principle, which if you took baby chem with me, you've already been familiar with, and you know that good old equilibrium Ethel is always, always, always watching. So we're seeing her poke her head in a little bit now. In case you weren't sure, these are the strong acids and strong bases here and here to refer back to when I go through my examples. All right, so looking at this reaction, we're gonna do a few things here. We're gonna identify our acid, our base, our conjugate acid, and our conjugate base, and then we're going to predict the direction that this reaction could go. All right, so to do that successfully, over here on the left-hand side, I see NH3 and H2O, all right? That NH3 became NH4+. So over the course of this reaction, NH3 gained a hydrogen. H2O, on the other hand, this one, we can see that that lost a hydrogen. All right, so knowing that information, we can predict which thing is which, because we know that Bronsted-Lowry acids donate a hydrogen. Therefore, since my water lost a hydrogen, that's my acid. I know that Bronsted-Lowry bases accept a hydrogen, and since NH3 gained a hydrogen over the course of my reaction, that is my base. Now, we know that our conjugates are defined as what our acid and our base turn into after that process has completed. So I know that NH3 gains a hydrogen, which means that it's going to turn into the conjugate acid. I know that H2O lost a hydrogen, which means it turns into a conjugate base. Now, the last step here is to predict what direction this reaction is going to go. So looking at these substances, ammonia, water, ammonium, and hydroxide, I don't see any strong acids or strong bases right off the bat. I don't see anything that's in these two tables. But what I do see is hydroxide. And so what I told you to do was if you didn't see any strong substances, you're going to treat either hydroxide, hydrogen, or ammonium as a strong thing. And so what we learned is the reaction is going to proceed away from the strongest thing, which means that this reaction is predominantly going to go left or backwards because our reaction is going to move away from the strongest thing that's there. All right, next one. So I see that HCl over the course of this reaction loses a hydrogen, and I see that water over the course of this reaction gains a hydrogen. All right, so I know that acids need to donate a hydrogen, so my HCl, since it lost a hydrogen, is going to be my acid. On the other side here, once it has lost that hydrogen, it's going to turn into the conjugate base. I know that bases tend to gain hydrogens or accept them, so that makes this thing my base. And over here, once that process is done, it's going to turn into the conjugate acid. My strong substance that I see here that's actively in the table is HCl. So you'll notice that this thing is in the strong acids and strong bases table. And because I've noticed that, I automatically know, hey, guess what? This reaction is going to move away from my strongest substance. So this reaction is going to proceed forward. Because I have a strong substance present, I'm going to ignore the H3O+, because as a reminder, you only pay attention to that if there are no other strong substances present in the reaction. But before I end this video, I just want to point something out. Looking at water, so let's switch colors really quickly. Looking at water here and here, you can see that water is acting in two different ways. In reaction 1 up here, water was your acid. In reaction 2 down here, water was your base. So that's proof that water can do either thing. It's amphoteric. It can either act as an acid and lose a hydrogen, or it can act as a base and gain one. If you have any issues understanding this, please let me know.